Hey students, Professor Nugent here. With this video, we start Chapter 7. We are looking at hypothesis tests and confidence intervals in multiple regression. In Chapter 7, we will look at the hypothesis tests and confidence intervals for one coefficient, joint hypothesis tests on multiple coefficients, other types of hypotheses involving multiple coefficients, confidence sets for multiple coefficients, and model specification, how to decide which variables to include in a regression model. In this video, we are focusing on hypothesis tests and confidence intervals for a single coefficient. Hypothesis tests and confidence intervals for a single coefficient in multiple regression follow the same logic and recipe as for the slope coefficient in a single regressor model. You can see here in the first point that our test statistic beta 1 hat minus expected value of beta 1 hat over the standard error is approximately distributed normal with a mean of 0 and variance of 1. So we have a standard normal distribution. So the hypotheses on beta 1 can be tested using the usual t-statistic. Confidence intervals are constructed like so. Here we have an example of the 95% confidence interval beta 1 hat plus or minus 1.96 times the standard error beta 1 hat. And we would do the same for all of the coefficients in our multiple regression model, beta 2 through beta k. Let's look at an example. In the first equation, number 1, we have a regression with only one regressor. We're regressing test score on the student-to-teacher ratio. In this regression, we have test score. The predicted value of test score, that's a hat, is equal to 698.9 minus 2.28 times the student-to-teacher ratio, where the standard error of the intercept is 10.4, the standard error of the coefficient on the student-to-teacher ratio is 0.52. In the second equation, we include the percent of students learning English. So now we are in the multiple regression model. The predicted value of the test score is equal to 686 minus 1.1 times the student-to-teacher ratio minus 0.65 times the percent of students learning English. The standard error of the intercept is 8.7, the standard error of the coefficient on the student-to-teacher ratio is 0.43, and the standard error of the coefficient on the percent of students learning English is 0.031. Observe that the coefficient on the student-to-teacher ratio in equation 2 is the effect on test score of a unit change in the student-to-teacher ratio holding constant the percentage of English learners in the district. That's what we're doing here when we include an additional variable in our regression, right? We want to know what is the effect of the student-teacher ratio on test score holding the other variables constant. And we see from equation 1 to equation 2, the effect of student-to-teacher ratio on test score falls by approximately 1/2, from 2.28 to 1.1. We can construct a 95% confidence interval for the coefficient on student-to-teacher ratio in 2 that is negative 1.1 plus or minus 1.96 times the standard error, which is 0.43, and that gives us a 95% confidence interval for the coefficient, the true population coefficient of negative 1.95 and negative 0.26. So we can say that we are 95% certain that the true coefficient on the student-to-teacher ratio will fall between negative 1.95 and negative 0.26 based on our sample and this sample regression. And because this confidence interval does not contain 0, this estimate, this OLS estimate, is statistically significant. The t-statistic testing the hypothesis that the OLS estimate, the coefficient on the student-to-teacher ratio, is equal to 0. The t-statistic is negative 1.1 divided by 0.43. That's the coefficient divided by the standard error, and that gives us negative 2.54. This is our t-statistic. which is greater, that's more extreme than negative 1.96. So we reject the hypothesis at the 5% significance level because our t-statistic is beyond the critical value. Let's look at the regression results. We regressed test score on student-to-teacher ratio and percent learning English, robust. So we're regressing with standard errors. So this is the familiar format where we regress y on x1, x2, so on and so forth, robust. Okay. And what do we want to look at? Let's focus on the coefficients and the standard errors, the p-values for now. So the coefficient of the student-to-teacher ratio, that's negative 1.1. The robust standard error is 0.43. Observe the p-value is 0.011. So it is very unlikely that we're going to find a t-statistic as large as this. It's very unlikely that we draw another sample that gives us a t-statistic as large as this. That's what this p-value is telling us. So that's why we have a statistically significant coefficient, because this p-value 0.01 is less than 0.05. Percent of students learning English, negative 0.649777. We have rounded that to 0.65 with the standard error of 0.031. We've plugged that in down here. And that p-value is even smaller. We've used heteroscedasticity robust standard errors for the exact same reason as in the case of a single regressor, that typically we are working with data that demonstrates heteroscedasticity, and even if we had homoscedasticity, there would be little to no penalty of using the heteroscedasticity robust standard errors. But if in fact we did have heteroscedasticity and used the homoscedasticity only standard errors, then we would have a problem. So we're using heteroscedasticity robust standard errors. And that is it for testing hypotheses about a single coefficient in multiple regression.